Okay, so you have a lab coming up on pendulums and using conservation of energy with pendulums. So let's talk a little bit about a pendulum. A basic pendulum would be a string or a rope with some sort of mass hanging down from it. Now, we assume a couple of things we're doing with pendulums. We assume that the rope itself is massless. We assume that there is no friction or air resistance. There's no friction at the hinge idea. So in our pendulum model, if I were to pull a pendulum back to some sort of initial angle here, what I assume is that that rope is going to maintain a constant length, so there's no stretch in the rope. And I assume that my point mass, that my pendulum bob is a point mass. So I don't generally have to worry about the actual size of it. Now, if it's not a point mass, like in a real lab, it's not a point mass, make sure you use the center of the pendulum bob itself as your measurement when you're looking for, say, the length of the rope. If I wanted to find the length of the rope, I would actually have to measure that all the way down until I got to the center there of the rope, because it's the center mass of that pendulum bob that is doing the oscillating. Now I'm going to assume that if I pull it back to this initial angle that it's going to move through an arc. That arc is part of a perfect circle, so it's actually undergoing circular motion, which we haven't talked about. We will get to that. And then I'm going to assume that because there's no friction or air resistance or anything, that it will go back to the original initial angle over here on this side. So it's going to keep oscillating between those same positions forever. Those are my assumptions. Now, there is a change in energy because we do have a change in height, and that's kind of the biggest thing we have to talk about. I'm going to exaggerate this arc here a little bit and move my pendulum bob down some so we can really see kind of the differences here. And if I pull it back to some initial angle, basically what I'm doing is I'm pulling it back to some height that is different than its starting height. So you can see that there is some sort of change in vertical position. Now, once again, I'm measuring that from the center of the pendulum bob, because in reality, I can't treat it as a point mass, but if we did, we would treat it as a point mass at the center of mass of the object. Now, there is going to be some change in height, but we're going to assume that the length of the string remains constant. So we're going to assume that the length of the string here is the same as the length of the string there. I didn't do that perfectly here, so I could exaggerate kind of those angles a little bit. Now, there's going to be some sort of change in height. When it gets up to this point up here, it's not going to be moving because it's changing directions, and anytime we have to change directions, we have to instantaneously come to rest. So at the ends of the pendulum, your speed is going to be 0 when it's at its maximum position. So where is it going to have its fastest speed? Well, its fastest speed is going to have to therefore be directly in between there. And the reason I know that its maximum speed has to occur here at the bottom is because I'm having a change in potential energy that is responsible for my change in speed. And because I've assumed there's no friction or air resistance or anything like that, I don't have any non-conservative forces. Well, what forces do I have? Ooh, is energy actually conserved? I'm talking about using conservation of energy, but is energy actually conserved? Well, let's take a look at the forces involved. Well, if I look at the forces, let's say I'm like right here, I have a tension force acting along the rope, and I have a gravitational force. Now, I know that my gravitational force is a conservative force, but what about tension? I don't have a tension potential energy or anything like that. So what about this tension? Well, if we take a look kind of at that arc that it was making, basically what I would do to determine if my tension was conservative or non-conservative is at that exact instant, I would create, I assume that my pendulum is moving with a velocity that is tangent to the circle. So when I'm moving in this circle, my velocity is always tangent to the circle. So that's one of the things that I have to assume. So basically I can resolve my axes into two directions, one that is parallel to that velocity, and then one that's actually parallel to my rope. So I actually have a 90-degree angle here between my tension force and my velocity. And no matter where I am here, I am always going to have a 90-degree angle between my tension and my velocity. So my displacement's always in the direction of my velocity. So if my velocity and displacement are in the same direction, and my tension is always perpendicular to my velocity, that means that my tension is always perpendicular to my displacement, which means my tension does no work. If it does no work, it's not going to do any work at any point. So when I go from A to B and then back to A again, I'm going to end up with a net work of 0. So tension does no work. Gravity is conservative, so it does 0 net work. So that means that this is a conservative situation since we have no non-conservative forces. Now, if we had air resistance, friction is a non-conservative force. So that's why we have to assume no air resistance here. So what this tells us is that we can use conservation of energy. And when I do conservation of energy, one of the first things I have to do is I have to define where potential energy is going to equal 0. Well, there could be ground down here somewhere, but I often don't care about where the ground is located. So when I choose my 0 height for my reference, I want to choose a value that is representative of my motion. So I'm going to set my potential energy equals 0 to be the lowest point in the motion. So I'm going to set that to equal y equals 0. And then I'm going to have some sort of y equals h to be my starting height. So when I pull it back at an angle. So I'm going to have y equals h there and y equals 0 down here at the bottom. But what is my h? Well, one thing that people tend to do is they tend to use the length of the rope or something like that as their change in angle. And that's not what's going on. Our h value is going to be the length of that portion of the rope, which is less than this whole length there. But we have an extra little tool, and that's we have a little triangle right here between the green length here, this portion of the length there, so that I have a 90-degree angle. So h is related by some value to my little value here. So for example, if I were to label that, if I were to label this section of the rope X, then L is going to equal H plus X. So if I could use this right triangle to find X, I'll know a lot of information. Well, X is going to be the adjacent side of that triangle. So X is going to be, and L's the hypotenuse, so it's going to be L cosine theta. So that means that L is equal to H plus X, which is going to be H plus L cosine theta. So if I wanted to solve for H is going to equal L minus L cosine theta, or H is going to equal L times 1 minus cosine theta. So if I wanted to be able to find that starting height, and I didn't know the height itself, but I knew my starting angle, and I should probably say those theta 0, because there are lots of possible angles, but that's my initial angle. So if I wanted to, and all I knew was the length of my rope and the angle, and I wanted to find what my change in potential energy is, I would have to know what that value H is right there. So if I knew that, how would I then solve the problem? So let's say I wanted to find the speed at the bottom. Well, since I have conservation of energy, I can apply that to the situation. So I would define maybe position 1 to be the starting position and position 2 to be this lowest point if I wanted to find the speed at the bottom. I could also do this at any other point in the motion and compare it to other points too. But a lot of times we're interested in that maximum speed. So if I'm looking for that maximum speed, then I would have K1 plus U1 is equal to K2 plus U2. And then my initial velocity is 0, so K1 is 0. And my velocity here at the bottom is maximum, but my potential energy is 0, so U2 is 0. So that tells me that mgh1 is equal to 1/2 mv2 squared. So mass cancels out. So actually the mass of my pendulum doesn't matter in this case. So if I had different masses of pendulums, it wouldn't matter. And then if I were to solve for V2, V2 is going to equal the square root of 2gh1. Well, oh my gosh, this is the exact same equation that we keep getting all the time. If I were to drop a ball from that height and I were to drop it straight down, the speed at the bottom would be 2gh1. If I were to have a frictionless ramp and it were to start, the box or whatever were to start from that height and go down to the ground, the speed at the bottom would be the square root of 2gh1. And now here we have another situation where I have a pendulum that's swinging, and if, like I said, I have to make that bigger. And if that pendulum bob starts off at this exact same initial height and goes to that exact same bottom of the ground, the speed is going to be the square root of 2gh. So basically the speed at the bottom, if I have only non-conservative forces and I'm not losing any energy anywhere, then all I need to know is my starting height to know my speed at the bottom. It doesn't matter what path I use to get there. That's super crazy powerful. So my square root of 2gh1 would be my speed at the bottom. So I could do that. Now in your lab, you're going to be using a photogate to measure the speed, and you're going to kind of be verifying that energy is actually conserved by going through kind of a process very similar to this. But remember that that most important thing here is that H1 value. That H1 value would be this weird L minus L cosine theta. And that's one of the biggest problems that people have, is they forget that step and they come up with something incorrect. So I hope that gives you a little feeling for the assumptions you have to make to do pendulums, for some of the things that you might need to consider during the motion, and some problem solving tips. Have a good day.